Yeah, hello.
Good evening, ma'am.
Good evening, beta. Am I audible?
Yes, ma'am.
Yeah, just a minute.
Yes.
Let me see whether I have opened the content for you or not yet.
Yes.
So I think yesterday we have learned about the Markovnikov rule and the anti-Markovnikov rule, correct?
Yes, ma'am.
Yeah. And even I guess we have learned about this. I asked you to take a screenshot of it and write down the things by yourself, isn't it?
Yes, ma'am.
Okay. So see what is given here. If my video isn't turned on, that's okay for you, right?
Yes, ma'am.
Because anyhow, like with video, we are not interacting with each other. Whatever is happening on the screen, that is important,
Yes, ma'am.
isn't it? Just a minute.
Yeah.
Fine. Now see here. When alkene means the hydrocarbon which contain carbon-carbon double bond, okay,
Yes, ma'am.
are heated with the bromine, chlorine at high temperature. Hydrogen atom of the allylic carbon is substituted with the halogen atom giving the allyl halide. Means like whenever alkene is there, alkene as a hydrocarbon we are using, here example is given. That is what CH2 double bond CH attached with the CH3, correct? Yes or no?
Yes.
Yeah.
Yeah.
So this carbon is a allylic because it is directly attached to carbon-carbon double bond and it is sp3, right?
Yes, ma'am.
sp3 hybridized. So one of the hydrogen from here would be lost and it will take a place of chlorine or bromine. Okay. So whenever it will be treated with the chlorine or the bromine, you will get the product CH2 double bond CH, single bond CH2 because one of the hydrogen from here would be lost and it will be attached with either chlorine or bromine as a product you will get. So this release hydrogen and the excessive chlorine will form HCl. Got it?
Yes.
Yeah. So this will be your like reaction. It's not a name reaction. It's just the halogenation. It's just what? Halogenation.
Halogenation.
Yeah.
Yes.
Now the next reaction which we are going to learn, that would be the halogen exchange reaction. Okay. In that the first name reaction we are going to learn, that would be Finkelstein reaction. This is a name reaction. What happened in this case? Alkyl halide is treated with the sodium iodide. Okay. Means alkyl halide, which one? Chlorine and bromine only, especially we are using here. The chlorides and bromides only would be. Alkyl iodides are prepared conveniently by treating alkyl chloride or a bromide with a sodium iodide. So this is a sodium iodide, right? And this will be alkyl chloride. Yeah?
Okay. Yeah.
This reaction takes place in presence of acetone. This is what? Organic solvent. Organic solvent. Correct. Now what happened? This chlorine has been replaced by sodium and this sodium will take this Cl to form a NaCl. As the solvent is organic, this your ionic compound does not dissolve in that and it forms precipitate, PPT. Okay?
Okay.
And that can be separated by the simple filtration technique. That can be separated by the simple filtration technique. Okay?
Yes, ma'am.
Yeah. And this reaction is called as the Finkelstein reaction. This is a name reaction which is called as Finkelstein reaction. Once again, see, alkyl halide and sodium iodide treated with each other. Like exchange of halogen takes place, iodine goes at the place of chlorine, chlorine come at the place of iodine. This reaction takes place in the presence of acetone. You will get alkyl iodide and sodium chloride or sodium bromide will be formed. It does not dissolve into organic solvent like acetone, hence get precipitate. So this is a name reaction. It is called as the Finkelstein reaction. Got it?
Yes, ma'am.
Please note down. Once you have done, let me know so I can scroll it down.
Yes, ma'am. Done.
See now next one, Squartz reaction. This is also a name reaction. In this case, alkyl, as we know that alkyl iodide preparation is quite hard because in a previous case, whenever we do the iodination of the hydrocarbon, that time that reaction is a reversible, right? Yes or no?
Yes.
We have already discussed it. And because of that, it is very hard to prepare the alkyl iodide. And hence, the Filkinstein's reaction is used to for the preparation of alkyl iodide. Okay.
Okay,
Here
ma'am.
you will get. And alkyl fluoride, we are not able to form by the fluorination of your hydrocarbon directly because that reaction is a poisonous and a lot of toxication will happen. It's a corrosive reaction, correct?
Yes, ma'am.
Yes or no?
Yes.
So for the fluorination, we are going to go for the another name reaction. That is what? Squartz reaction. What it is?
Squats.
Squartz reaction. In this case, what happened? Alkyl fluorides are prepared by heating alkyl chloride or a bromide with a metal fluorides. Metal fluorides are what? Like silver fluoride AgF, then mercuric fluoride Hg2F2, then arsenic fluoride, or we can say arsenic trifluoride AsF3, antimony trifluoride SbF3, etc. So these all are metals, right? Ag, mercury, like silver, mercury, arsenic, and the antimony. These are all what? Metals.
Metals.
So these are the metal fluorides. So when you treat this alkyl halide, especially alkyl chloride or alkyl bromide with the metal fluorides, what happens? This fluorine and chlorine will get exchanged. Exactly same reaction how it was happened earlier. It will happen in this case. Only the thing is what instead of iodine here, what happened? Fluorine will get exchanged, right? You will
Yes.
get alkyl fluoride and silver chloride would be formed as a precipitate. Okay. Only the thing is what you need not to use any sort of solvent. Earlier you have used the solvent of acetone, right?
Yes, ma'am.
Solvent need not to use in this case. And this name reaction is called as Squartz reaction. Please note down.
Done, ma'am.
Now, next thing which we are going to see, that is the electrophilic substitution. So you have to know what is the electrophile. Earlier, I have explained you about the nucleophile. When I have in a demo class, right? SN1 and SN2, when I have
Yes,
explained
ma'am.
you, that time I have explained you about nucleophile. So nucleophile and electrophile, these are completely opposite species. Nucleophile is electron rich and electrophile is electron deficient. Okay. Understood?
Yes, ma'am.
Yes or no? Nucleophile is what? Electron rich species.
Rich. Yeah.
Yes. And electrophile is electron deficient. Okay,
Yes.
fine. So, electrophilic substitution means what? Like electrophilic deficient species should be attached to your aromatic ring. That is called as the electrophilic substitution. Okay. And it
Yes.
will be what? Like it will be involved in the preparation of haloarenes using electrophilic substitution because electrophilic substitution can be happen on an aromatic ring. So
Yeah.
aromatic ring will be substituted with halogen when this reaction will be takes place. And hence, what happened? It involved the preparation of haloarenes. Okay. It
Yes.
involved preparation of haloarenes. Yeah. Just a minute.
Yes, ma'am.
Hello. Okay.
Yes.
I'm going to stop the sharing of this because I'm going to explain you about the electrophilic substitution on a whiteboard. Okay?
Okay, ma'am.
Just a minute. Um, yeah. Yeah. Mhm. Fine. Whiteboard is visible to you now?
Yes, ma'am.
Okay. Now see in this case, what happened here? You need to just reduce the thickness. Fine. Okay. So this is a benzene ring, correct?
Yes, ma'am.
Yeah. What is the characteristics of this benzene ring? It has alternate,
Double bonds.
right?
Yeah.
Another thing is what? It is planar, right?
Yeah.
And each corner consists what? One of the hydrogen, correct?
Yes.
Hydrogen, 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 and the hydrogen present over here, correct? This is a
Yes.
benzene structure. Because if you see the molecular formula for benzene, that is C6H6, correct?
Yes, ma'am. Yeah.
Yeah. So what happened if one of the hydrogen from this would be replaced with electrophile, right? That time it will undergo electrophilic substitution, correct?
Ma'am, why with an electrophile?
Because it is electron deficient species. Like this is a reagent. I'm giving you a general example.
Okay.
This is completely general, okay? So rest all hydrogen would be as it is. Either I'll show or I won't show hydrogen is present over there. That you need to consider, okay?
Yes.
Yeah. So electrophile is what? Electron deficient species, correct?
Yes, ma'am.
Already we have learned about it. But then what happened? There must be a question in your mind why these electron can like why benzene can opt for the electrophilic substitution, because
Yeah.
benzene itself is a electron rich. Benzene is what? Electron rich, correct?
Yes, ma'am.
Why it is electron rich? Because if you see the structure of benzene, common structure of benzene, suppose this would be the 6 carbons, okay? Each have this pi bonds, correct?
Yes, ma'am.
Yeah. And because of that, what happened? There would be the overlapping of these can form a double bond. 3, correct?
Yes, ma'am.
So benzene have a cloud of electron.
Okay. Got it.
Okay. So number of electrons are present. Electrophile is electron deficient. It has a lot of electron, correct? And
Yes.
hence it can be readily react with electrophile. Opposite attract, that is the rule, right?
Yes, ma'am.
Yeah. And because of that, what happened? Benzene readily react with electrophile. Now, normally electrophile can be goes to the benzene and you will get the substituted benzene. This will be what? Substituted benzene, correct?
Yes, ma'am. Substitute bonds.
But then what if there is a already substituent present on the benzene? Then where electrophilic substitution would take place? That is the question, isn't it?
Ma'am, can I repeat?
If already substituent is present on a benzene, suppose benzene is like
Okay.
this. It has a CH3 group on it, right?
Okay. Yeah.
So where your electrophile would go? Suppose you have gone opt for the electrophilic substitution. So what would be the product, right?
Ma'am, it can attach to the methyl group, right?
Are you sure? It won't happen in that manner because methyl group is not that electron rich how your benzene ring is. But then because of the presence of this methyl group, your positions of benzene ring would be definitely influence. How it influence that I'm going to explain you. So whatever I have written here, I hope you have written in your notebook simultaneously with me.
Yes, ma'am.
Okay, shall I erase it then?
Yes, ma'am.
Okay. Just a minute. Let me erase it. I'll explain you that scenario as well. Okay.
Okay.
Okay. Only this much is remained. Let's see. Delete that too. Okay. Now here see about it. The reaction benzene. The substituent which is present on your benzene, it will either activate your benzene ring or deactivate your benzene ring. Okay. Hansini, are you there?
Yeah.
The substituent which is present on your benzene ring, either it will activate your benzene ring or deactivate your benzene ring.
Okay, ma'am.
So activating means what? If it is electron donating group, then the ortho para position will become electron rich. Okay. And if it is electron withdrawing, that time your ortho and para position become electron deficient. Okay.
Okay.
I'll write
Ortho,
here.
meta, para become electron deficient when, ma'am?
Where? Ortho and para, na?
Yeah.
Yes. Whenever your group is electron withdrawing group. This is electron donating group. Okay. And this will be electron withdrawing group. Understanding? So the group which is present on your benzene ring, either it will activate your benzene ring or it can be deactivate your benzene ring. Okay. If it is electron donating group, it will activate your ortho and para position. And if it is electron withdrawing group, it will deactivate your ortho and para position. Understanding?
Ma'am, activate in the sense?
Activate in the sense what? I'll let you know for this. Like I'll write the canonical forms for this group. And even for this, you will understand how it will be activate and deactivate. Okay?
Okay, ma'am.
Fine. Now, this is your benzene structure, right? Here is
Yes.
a CH3, which has 3 hydrogens on it, correct?
Yeah.
Yeah. So these hydrogens and this ring is in hyperconjugation. Hydrogens are in hyperconjugation and carbon directly attached to your benzene ring. It gives your electron donating inductive effect. Okay.
Okay. Yes.
Electron donating inductive effect, correct? Now what happens? This hydrogen, as it is in hyperconjugation, it will form double bond in between carbon and the carbon of ring. Correct? Yes?
Okay. Yes, ma'am.
Yeah. And because of that, what happened? This double bond will be shift over here. Correct? You will get the canonical form in this way. These double bond as it
Ma'am,
is, it
this is
doesn't
when the substituent group is electron withdrawing.
donating. It's about donating. CH3, no? Here we have written electron donating group.
Okay, ma'am. So when it's donating, the bond shifts.
Bond shifts. No, even in withdrawing also bond shifts, but then how it will be shift, that matters.
Okay.
Okay, fine. Now here what happened, beta? Now here what happened? Hydrogen form a carbon-carbon double bond. I'm going to write here double bond, okay? Right? Hydrogen and hydrogen. And this hydrogen will be in a close proximity. It won't go away. It will stay there only, nearby. Okay?
Okay, ma'am.
Fine. Yeah. Now what happened? This double bond is shifted here on this carbon and it will generate the negative charge, correct?
Okay, so because it shifts, it
It become
generates
electron rich, right? Ortho position become electron rich,
rich.
correct? Now, what happened? This negative charge again form a double bond here inside, and this double bond would be shift at the para position. Clear?
Oh, okay, got it.
Yeah. Another canonical form, what you will get here, then this newly formed double bond. This is previous double bond as it is, and this double bond has been shifted at a para position with a negative charge. And whatever structure is up, that will be as it is. Correct?
Ma'am, I have one doubt.
Please ask.
Ma'am, from ortho, where does it shift?
Sorry?
From ortho,
Huh.
where does it shift next?
It goes in between the carbon. Suppose it was in a 1 and 2 carbon earlier, right?
Yes, ma'am.
1 and 2 carbon it was. It goes to the ortho, right? Now it
Yeah.
goes into the 2 and 3 carbon, right? And
Oh.
bond in between 3 and 4 carbon will be shifted at the para position here.
Okay, ma'am.
Got it?
Yes.
Now, what happened? And it will form a bond. So that newly formed bond is here. Okay? This is your previous bond, and this is a negative charge at the para position. This is your structure 1. This is your structure 2. Correct?
Yes, ma'am.
Now again, what happened? It is in between 3 and 4 carbon. It will shift into again 4 and 5 carbon. Right? And the bond in between 5 and 6 carbon will be shift onto the 6th carbon.
Ma'am, because it makes a double bond with the carbon, that's why it becomes electron rich at ortho.
Fine. Understanding or not?
Yes, ma'am. So
Now it come where exactly now? At the ortho position,
ortho.
correct?
Yes.
Yeah. So I can write it in this manner. Again, canonical form I'm going to draw. Here it will be negative charge, okay? Double bond C, H, H, okay? Fine.
Yes.
This would be the third structure, okay? And the last, hydrogen would be in the close proximity. It will go back over here, and this double bond is shifted back in between carbon and hydrogen. You will get the structure like this. Got it? So you see your this structure, suppose this is your structure A and this is your structure B, okay? Hansini?
Yes, ma'am.
Just check, this is a structure A and this is structure B, correct?
Yes, ma'am.
Yeah. So if you see structure A is equal to structure B.
B.
Now what happens, see, these double bond positions of A and B is completely different, correct? But then structure is same. Yeah?
Yes. Yeah.
And these all are canonical forms. In these canonical forms, first, second, and third, what you come to know? This is at what? Ortho, para, and ortho.
Ma'am, if the double bond of the carbon is not formed with the substituent group, then it won't, this all won't happen, right?
It's not, that's what I said. Na? It should be electron donating group. If it is electron donating group, then only it can form the double bond.
Okay.
If it won't be electron donating, that time what happened? It will take an electron from that same position. We are going to check it with the nitro group NO2.
Okay.
Correct? Yes?
Yes, ma'am.
So this is about what? Only electron donating group if it is present, that time only. So what all of electron donating group? If OH group is present, it has a lone pair, correct on it?
Yes, ma'am.
It will be donate the electron to form oxygen and the carbon double bond. If there would be NH2, amine group, that time also it will form, correct?
Yes, ma'am.
Yeah, so like that, if electron donating group present, that time only you will get 1, 2, 3 canonical forms where ortho and para position is electron rich. And hence, whatever electron deficient group will become in close proximity of the benzene or react with the benzene, it will come at the place of either ortho or para.
Para.
Got it? Yes. Meta product you will not get with electron donating group. Understood?
Okay.
Yes. So I hope you have written all this.
Yes, ma'am. Yeah.
Okay, so shall we see for the nitro group?
Yeah, ma'am.
Okay, electron withdrawing things.
Ma'am, what are the electron donating and the electron withdrawing groups?
That's what I said. Electron donating is like this CH3. Any alkyl group is inductive, shows electron donating inductive effect, right?
Yes.
OH is also shows the electron donating inductive effect, and at the same time, lone pair is present onto the OH, right?
Yes,
These
ma'am.
lone pairs are really very important, and even the nitro group, it is also have nitrogen group is also have a lone pair on it, correct?
Yeah.
Yeah. So these all are what? Electron donating. Any group which can donate the electron to the ring is electron donating group. And the one which can withdraw electron from the benzene or the ring, that are what? Electron withdrawing group. Okay.
Ma'am, can you give us few examples of electron withdrawing?
You want to, I should give you some more examples.
Yes, ma'am, for electron withdrawing, not for donating.
Withdrawing, yes. Nitro group is there, right?
Yeah, ma'am, nitro is not donating.
No, it is withdrawing. This NO2 is withdrawing, but then NH2 is donating.
Okay.
Okay. Yeah, don't get confused in between. It is very important and it will come by the practice. So I'll do one thing. Once class is done, just remind me once in a group. I'll post the number of electron donating and the withdrawing groups list.
Okay, ma'am.
Okay, fine. So shall I erase it?
Yes, ma'am.
Yeah. Now this nitro group, how it is electron withdrawing, I'll let you know. Okay.
Okay.
Okay. Hmm. Hmm. हाँ नहीं ले बाबू को ले उधर बाहर बैठ बैठो थोड़ी देर एक 5 मिनट 5 10 15 मिनट दीदी दीदी का क्लास खत्म है दीदी जाओ ले लो उसको बाहर के रूम में बैठो जाओ Go. This is a benzene ring, okay.
Yes, ma'am.
Now I'm going to just keep it here, and nitro group will be N double bond O, here O minus, correct?
Yeah, ma'am.
Yeah. Now in this case, what happened? And this bond would be shift here to nitrogen as it has a conjugation with oxygen. Okay.
Ma'am, could you repeat?
Yeah, sure. I'll explain it again. Check it once.
Yes.
This is your benzene ring. Okay. Here is a nitrogen. Nitro group would be either nitrogen oxygen double bond and nitrogen oxygen single bond with a negative charge. This is a nitro group actually, NO2. Correct?
Okay. Yeah.
Now what happened? This nitro group is electron withdrawing because this double bond and this double bond is in conjugation. I'll show you with a different color. This double bond and this double bond is in conjugation because double, single, double, double like that bonds are there, right?
Yes, ma'am.
Right. So what happened? It will form a double bond over here and this double bond would be shift on the oxygen, correct?
Yes, ma'am.
Yeah. Now what you will get in this case, canonical form should be always shown by the double-headed arrow, okay?
Okay, ma'am.
Now what? This double bond is shifted in between nitrogen and carbon. Here it will be nitrogen and carbon double bond, okay? On oxygen, there is a negative charge generated. Here it is oxygen, okay, with negative charge already. Correct? Now what
Yes.
happened? These two bonds would be as it is, but then from here double bond has been shifted in between carbon and nitrogen. So this carbon become electron deficient. So it generate a positive charge. Correct?
Oh, yes, yes, ma'am.
Correct.
Yeah,
Now to satisfy this positive charge, this double bond would be shift here, right? In between these
yeah,
two carbon, in between these two carbon,
yeah,
right? So this would be your first structure. In second structure, what happened? Here double bond, here double bond. This double bond as it is, this is newly formed double bond. And this double bond shifted in between these two. So here it form a positive charge, correct?
yes, ma'am.
Here it will be nitrogen, oxygen with negative charge. Here also oxygen with negative charge, correct?
Yes.
This
Ma'am,
will be your
1 second,
second.
could I draw this? Just a second.
Yeah, you have to. I'll give you time to draw, don't worry.
Okay.
Yeah. Now in next case, what happened? Here is a positive charge, right? Already this is newly formed bond, so it won't break immediately. So this is a previous bond. It will try to satisfy this positive charge. And what happened? It will form a bond in between these two carbon, correct? And because of that, you will get the third structure in this way. Double bond. Here also double bond. And as double bond is shifted, here it become a positive. And rest all structure as it is double bonded nitrogen, O minus, O minus. Correct?
Yes, ma'am.
Yeah. Now what happened? To satisfy this positive charge, this like double bond has been shifted over here. Okay.
Yes.
Yeah. And if it has happened, like nitrogen would become deficient 1, 2, 3, right? Yes or
Ye-
no? And to satisfy it, to like promote it, this oxygen would be shifted here. Like either this or that, any of the oxygen will form double bond in between nitrogen and oxygen, and this promote this double bond to shift back into the ring.
Ma'am,
This
could
is
you
your
repeat
third
this
structure.
part?
Yeah. Like we need a driving force to shift the double bond into the ring, right? At this
Yes,
place.
ma'am. Yeah.
And that is given by this negative charge. This negative charge would be form a double bond in between nitrogen and oxygen. And immediately then this double bond, like nitrogen and carbon double bond is shifted in
Okay.
between carbon and carbon. Okay. To satisfy this positive charge.
Okay.
Now you will get the new structure that will be like this. 1, 2, 3. Okay. N. Here it will be double bond O and O minus. Correct? So this is your structure A. This is your structure B. If you see the structure A and B, A is equal to B. Correct? Because only just the position of double bond is different. Like here 1 and 2 has double bond. Here 2 and 3 has double bond alternatively. Correct?
Yes, ma'am.
Entire structure is same. Correct?
Ma'am, I have one doubt.
Please ask.
Ma'am, in the third structure, the double bond moved inside the ring, right? The double bond
Yeah,
between the
yeah.
nitrogen and carbon.
Yes.
Ma'am, then how did we still have a double bond with the oxygen above?
Because oxygen has a negative charge over here, no?
Oh,
This
okay.
negative charge is shifted between nitrogen and oxygen because already double bond was there, and to like forming a double bond in between carbon and nitrogen, this bond has been shifted here, and this double bond has been shifted on the head, and that will be act as a negative charge in the entire session. See here, negative, negative, and the negative. Okay, and that negative charge again come back into the oxygen and nitrogen as a double bond.
Okay, ma'am, got it. Yeah.
Got it?
Yeah.
Fine. Now say this is A and B. What happened when there is an electron donating? This group is what? Electron withdrawing group. Okay, this won't be electron donating. Electron withdrawing group. It withdraws the electron, correct?
Yes, ma'am.
And because of that, your like structure 1, 2, and 3 itself suggests that your ortho, para, and ortho position becomes how? Electron deficient, correct?
Yes, ma'am.
Yeah. So electrophile will not go at ortho and para position when there is an electron withdrawing group. It will attack where? On meta position.
Meta.
Because meta is electron rich in this case. Keep it
Okay.
in your mind. Okay.
Yes, ma'am.
Only meta is electron rich because ortho and para become deficient when there is electron withdrawing group. Clear?
Yes, ma'am. I'll just
If you
draw this, ma'am. One second.
sorry,
Can I just draw this, ma'am?
yeah, you can. And once you have done, let me know. So
Yes.
we will go back to the electron donating and withdrawing groups. You can note down at least about it.
Yes, ma'am. Done, ma'am.
Just a minute. Let me erase this all. No, I supposed to go back to our PDF, right?
Yes.
Yeah. Now see here, what is given about the electrophilic. Because of that only I have explained you the background, which is missing in the PDF. In a PDF, all these things are not given. Okay.
Yes, ma'am.
So see what is given in this case about the electrophilic substitution. Preparation of haloarenes using electrophilic substitution. What they said, when arene is treated, arene means aromatic compound, okay? Any arene is nothing but an aromatic compound. When arene is treated with chlorine or bromine in a dark at ordinary temperature in the presence of Lewis acid catalyst. Lewis acid catalyst can be iron, can be iron halide like FeCl3 or anhydrous aluminum chloride AlCl3. Aryl chloride or aryl bromide is formed. So these are what Lewis acid catalyst. Please note down. It is important. Okay.
Ma'am,
When
what are they?
Lewis acid catalyst. Lewis acid catalyst.
Okay.
Iron, FeCl3 or AlCl3, and both should be anhydrous. Okay.
Yes,
Yeah.
ma'am.
So here they have given when toluene is brominated in a dark at ordinary temperature in presence of iron, a mixture of ortho and para bromotoluene, toluene it should be, toluene
Yes.
is obtained. Okay. Why ortho and para? Because ortho and para only activated due to electron donating electron donating group. Okay. Yeah. Clear?
Yes.
Fine. Now what they said here, see about ortho and para isomer can be easily separated as there is a large difference in their melting point. Ortho and para isomers, okay, they can be separated either distillation or the fractional distillation technique. Then aromatic electrophilic substitution with iodine is reversible and hence we are not opt for it. Okay. In
Yes.
this case, use of HNO3 and HiO4 removes Hi by oxidation of I2. And hence equilibrium is shifted to right and iodo product is formed. Means in this case, what you have to use? You have to use nitric acid in presence of hypohalide acid like HiO4. These two mixtures you should use. It will remove the hydrogen iodide from the reaction and hence your reaction will shift into the right hand side. Because as we know that Hi is what? Strong reducing agent.
Strong reducing agent.
Immediately reduce that iodobenzene back into the benzene, correct?
Yes.
And hence at HNO3 and HiO4 act as oxidizing agent. It will be oxidized Hi into HiO4 and your equation will be shift to the right hand side. Means you will get the expected product, that is iodo product. Okay. Now
Okay.
next one is about fluorine. They have given F2 being highly reactive. Fluoro compounds are not prepared by this method. Okay. Fluoro compounds cannot be prepared by this method.
Yes.
Okay. So if you want to note down about it, you can.
Ma'am, one second.
Yeah. If you have done, let me know. If I supposed to scroll, that too you tell me.
Done, ma'am.
Wait a minute. Yeah, I understood. Listen, ma'am. I understood that all things. Just a minute, Hasini.
Yes.
Okay. Sorry for disturbance, beta. Okay.
Yes.
Yeah. I was explaining you what? Yeah, I asked you to note it down, right? Have you
Yes.
noted?
Yeah.
Yeah, fine. Now we are going to see about the Sandmia's reaction, correct?
Yes, ma'am.
Yeah, so this is a name reaction and it's very important. It is present in your amine chapter. This is present into your haloarenes and haloalkanes. And it's like, it's one of the important reaction. In this, what you have to do, you have to do the diazodization first. Okay. And diazodization would be done with the help of what your HX, NE, with your HNO2.
Okay.
You might be confused like why HNO2, why not HNO3? HNO3 is what? Nitric acid. But then here you have to take a nitrous acid, not nitric acid. Okay.
Okay, ma'am.
Hmm. So I'll let you know what exactly happened in this reaction. See, what is given, we will read it once, but then mechanism I'll give you from my side.
Okay.
Yeah. See, aryl halides are most commonly prepared by replacement of nitrogen of diazonium salt. Right. Means if aryl group is there with a nitrogen on the head here N2 that can be replaced with easily halogen. Okay. And you will get your aryl halides. Correct?
Yes, ma'am.
This is the meaning of sentence. When a primary aromatic amine like aniline, what is the structure of aniline? Like this, your benzene ring substituted with NH2 group. This is what your aniline structure. Okay.
Yeah.
Suspected in a cold HCl is treated with a sodium nitrite. Sodium nitrite, like nitric acid, we have nitrous, we have seen, no? Nitrous acid, HNO2.
Yes.
Sodium nitrite is have same role. Okay. A diazonium salt. When HCl and NaNO2 react with each other, it will form a diazonium salt. That is benzene diazonium chloride. Right.
Ma'am,
This is
when
the
HCl
benzene.
reacts with sodium nitrate.
Yes.
Okay.
NaNO2 plus HCl. This Na and this Cl will form NaCl. and this H and NO2 form HNO2, but then we don't want HNO2. It will form a H2O and you will get NO as a nitronium ion with positive charge over here. Understanding?
Ma'am, so H2O plus NaCl and then
It acts as a electrophile.
okay, ma'am.
Yeah, means like electrophile will be generated in C2. In C2 already we have seen when
Yeah.
two reagents react with each other to form a compound which will be take part into the chemical reaction. And
Yes,
it happen in the chemical reaction, it is called in a C2.
C2.
Okay?
Yeah.
Right. And it is a electrophile which has a positive charge. And as we know that aniline, it has a negative charge, like lone pair over here. It is what? Electron donating. And it has an electron donating inductive effect, or even we can say electron resonating effect also, because it has a lone pair also to donate.
Okay.
Correct? Yeah. So strong ortho para directing product you will get your halogen, which will be remove this nitrogen. It will goes either at the ortho position or at the para position. Correct?
Yes, ma'am.
Yeah. So how this electrophile form, how this electrophile will be attacked by the benzene, that all process in detail I'm going to explain you with the mechanism. Okay. That is missing in the PDF. Okay. Here they
Yeah.
have directly explained what happens. When diazonium salt is treated, cuprous chloride, whatever diazonium salt they have made, this is, it will be treated with what? Cu2, Cl2. Correct.
Okay. Yeah.
So this Cl2 is act as a halide X or X2. It has replaced this part and nitrogen, and whatever Cl would be like Cu would be there. This Cl would be go and sit at with the Cu. Again, your catalyst would be remain as it is. CuCl2 would be remain as it is. It
Okay.
won't go anywhere. Correct.
Yeah.
One of the Cl would be removed and it take a place of this, and this N2 would be removed completely. Correct. And you
Ma'am,
will get
so this is happening in the presence of NaNO2 and HCl.
no. NaNO2 HCl would be used to prepare only this compound.
Okay.
So once you get the diazonium salt, the second reaction is what? CuCl2. From that Cl2, one of the Cl come at this place and this N2 would be removed completely.
This is formed in the situ or we add this?
No, we are adding this. It
Okay.
won't form in a C2. This
Okay.
will be form in a C2. Means NO, whatever we are going to form, no, with positive charge. That is
Yeah.
formed in C2. This won't form in C2. Okay?
Okay.
Yeah. So the first reaction is a diazodization reaction. Diazonium chloride would be formed in this. It's not a Sandmeyer reaction. But then from the diazonium salt, as you are forming chlorobenzene, this reaction is called as the Sandmeyer reaction. Got it?
Yeah. Yes, ma'am. Got it.
Yeah. So this is little confusing reaction. It won't understand within a minute. It will take a time. Okay. So this I will explain you in tomorrow's class thoroughly from the preparation of your electrophile, like how the attack of benzene would happen on the electrophile and how you will get the ortho and para directing products. Okay.
Okay, I got it.
Yeah. So I hope whatever I have explained that is sufficient and understandable to you.
Yes,
Today's
ma'am.
class.
Yes.
Yeah. So that's quartz reaction. After that, the one Filkisten's reaction. For that, different compound you check and please try to solve the more examples of it. If possible, I will post few questions regarding. Please go through it and try to solve.
Yes, ma'am.
If you're not able to, please make a note of it and in the next class, ask the question regarding. Definitely, I'll help you to solve this. Okay.
Ma'am, if
Yeah.
possible, can you send few questions?
Yeah, you can send me question if you have any point, like this point is not understand, that is not understand, or something like this is a question regarding the topic we have covered, but then I'm not getting the answer. You can post in a group or else you can personally send me.
No, ma'am. I mean, if you have any questions regarding this topic, can you please send me?
I have n number of, I'll share with you, don't worry.
Okay, ma'am. Thank you so much,
Yeah.
ma'am.
Give me a day, means by evening I'll do, okay? When I'll be free.
ma'am.
Yeah?
Yes, ma'am. Thank you,
Yeah.
ma'am.
Most welcome, beta.
Okay.
Take care, beta. Bye.